The third law of thermodynamics defines absolute entropy. So the third law says that the entropy for a perfect crystal at 0 Kelvin is 0. This allows us to have an absolute 0 point. So that the absolute entropy is the amount of energy that is due to the dispersion of energy through its particles. And this allows us to say that entropies are always a positive value. In order to compare the entropies of different substances, it is helpful to define standard conditions. And so standard conditions are defined as a set of conditions, such as for a gas, it has to be at 1 atmosphere. If it's a liquid or a solid, it's for 1 atmospheric pressure and a temperature of interest, which is usually 25 degrees Celsius, which is why we have 298 Kelvin that is represented. And then if it's a solution, it needs to be 1 molar solution. And so the way we know it's standard is we have this little degree symbol as a superscript. This is an extensive property, so entropies, the more of a substance you have, the more entropy is possible. And we define it as standard molar entropy so that we're looking at 1 mole of the substance. And these standard molar entropies do change if we change state. So if we go from solid to liquid to gas, they also change for different allotropes. And allotropes are different ways that the atoms are arranged for a particular complexity, molar mass, and also degree of dissolution, which we'll look at a little bit more in depth in just a minute. There are tables of standard molar entropies that you can find. You'll notice that the units that we have are joules per mole Kelvin because it's a molar entropy. And we'll look at how these values change depending on the substance. But these are standards that you can find either at the back of your book or in table values in homework problems or other references. If we change the state, and we've already talked a little bit about this in this chapter, the more disorder or more randomness that is possible, the higher the entropy. And so if we look at water as a liquid or water as a gas, because gases have more randomness, our entropy, our standard molar entropy is higher. If we increase the molar mass, our molar entropies also increase. Now this doesn't generally have as large a value as some of the other changes that we're looking at. So on the last slide when we were looking liquid to gas, the values had a much larger difference in molar entropies. But the mass does make a difference. So the larger the molar mass, the larger the entropy, and that's because heavier atoms tend to be closer to each other, allowing the dispersal of energy. Allotropes, again, are same element but attached in different ways. So we have, in this case, carbon as a diamond, which has a tetrahedral structure to it, or carbon as graphite, which lays in flat planes, and those flat planes can slide across each other, which is why pencil lead works the way it does. It slides off layers of the graphite. And so because it is less constrained as graphite, it has a larger molar entropy. If we increase the complexity, So typically the more bonds that are present, the larger the molar entropy. So here we have argon and nitrogen monoxide. Even though nitrogen monoxide has a smaller molar mass, its entropy is higher because there is a bond between the two, between the nitrogen and the oxygen. Argon, as a noble gas, has no bonds. And the more complex our molecules become, the more bonds that are present, the higher the molar entropy. So although carbon monoxide and ethene are very close in molar mass, because there is more bonds in the ethene, it has a higher molar entropy compared to our carbon monoxide. If we look at a simple molecule like nitrogen monoxide, we only have 2 atoms that are involved, but we have bonds between them. And there's more places for the energy to be in the gaseous nitrogen monoxide. So we have translational motion, which is motion that as it's moving in straight lines. So we have motion along the x-axis. We can have motion along the y-axis or coming out of the page towards us as the z-axis. This simple molecule can also rotate, so it can move in circles around. And we also have vibrational motion, which is present in all atoms and all substances, but now those bonds can be shortened or lengthened through that vibration. And because there are these additional places for energy, that is what increases our entropy. If we dissolve solids, that also increases the entropy, because now we have gone from a crystal structure and moved those ions into a solution, giving them more freedom of motion. So here we have the exact same substance, but one as a solid and the other dissolved in solution. And when it is dissolved in solution, because it has more randomness, more disorder, we have a higher standard entropy of dissolution.